Now, let's talk about a related concept. This is called the apparent brightness of a star. The apparent brightness of the star is the amount of energy received per unit area, that is to say 1 square meter, by some detector at a distance. Now, one thing that you should have a very simple understanding of is the fact that as you move farther from the star, it will appear to be brighter. And this is where the word apparent comes from, because obviously depending on how close or how far you are, the star will appear to be brighter or dimmer. So if we imagine that the light from a star emanating outward, so we might have some unit area here, and I might have some distance, but if I go out to twice that distance, if this has an area of 1, this would have an area of 4. It will be 4 times greater area. If I go 3 times farther away, this will cover 9 times the area. Now, what's important about that is it's the same amount of light goes through this box, which has a unit area of 1, as goes through this box, which has a unit area of 4. That means that this light will appear dimmer. The light will essentially have been more spread out than the light back here. So this means that 1 square meter here will capture possibly 1 unit, but 1 square meter here will only capture 0.25, or a quarter of a unit. So each square meter, as I get farther away, is capturing a smaller and smaller amount of energy. And essentially you might think of the star, and we're out at some distance away, and I have a little detector down here, and I'm going to capture 1 square meter worth of light, and I'm going to see, and I'm essentially going to count how much light has hit that 1 square meter. And then with that information, then I can sort of work out the distance for the star, because apparent brightness is the amount of energy received per unit square meter by a detector. So that means that the formula, the letter lowercase b, represents the apparent brightness. That means that what I would need to do to figure out how much energy is going to hit this square meter is I need to take the total amount of energy leaving the star, right? So that's called the luminosity of the star, and I need to divide it by the formula for the surface area of a sphere. Now in this case, I'm not talking about the surface area of the star. I'm talking about the surface area of an imaginary sphere that's at some distance r away from the star where my detector is located. And so that's why the formula is 4 pi d squared. So remember, the surface area formula, we go back to here, the surface area formula is 4 pi r squared. So that's where the 4 pi d squared comes from. It's the formula for the surface area. So if I take the total luminosity, I divide it by the surface area of this imaginary sphere at some distance r, this thing will produce units of watts per square meter, and this is the measure of the apparent brightness of the star. It's how bright the star will appear. So now, for example, if I measured the apparent brightness and I knew the distance to the star, I could figure out the real or actual luminosity of the star. This is really crucial, because if I don't know the distance, then this apparent brightness is not really that useful. It really won't tell me anything. It just tells me how bright the star appears to be from our skies. But without knowing the distance information, I can't turn that into luminosity. And the luminosity, of course, is the most important aspect of the star, the total amount of energy that the star gives off. It's a measure of what's going on, most directly a measure of what's going on in that star, whereas the apparent brightness doesn't really tell me anything about the star other than how bright it appears at some distance. So it's really crucial that I know that distance. This is how the formula is ultimately used, generally speaking, is that we can measure this. That is to say, I take a detector and I measure how much light hits 1 square meter of this detector, and then if I know the distance to the object, I can calculate the luminosity of the object. Now, don't forget that we already have a formula for the luminosity, so that means I could write a more general formula for apparent brightness, and that is by combining together the the luminosity of the star, which is the sigma a t to the 4th over 4 pi d squared. I get two formulas for the apparent brightness of a star. And what's nice about this one is that if I, for example, can calculate the luminosity of the star, then I can calculate, for example, the temperature, the surface temperature, if I know how big the star is. So these two formulas are both very useful. You'll be asked to solve example problems for any one of these guys. Okay? So, remembering that, we can take a look at some of the example problems. So this is question 1 on page 496. They tell you that they have a star, a radius of star A is 3 times that of star B. So that means that RA is equal to 3 times RB. And they tell you that its temperature is double that of star B. So that means that the temperature of A is equal to twice the temperature of B. And what they ask us is to find the ratio of the luminosity of star A to star B. So the luminosity formula is sigma A T to the 4th over, this would be the luminosity of A, over the luminosity of B, which is, sorry, let's make this a little more clear. Luminosity A over luminosity B would be sigma A T to the 4th. But this would be the area of A and the area of B and the area of A and the temperature of A and temperature of B. Now remember, there's a formula for the surface area of a star, and that is sigma 4 pi R A squared times TA squared. Down here I have sigma 4 pi R B squared TB squared. Now obviously these cancel, this cancels, so it comes down to these two. But I know that the radius of A is 3 times the radius of B. So in parentheses, let me put 3RB squared. And I know that the temperature of A is twice the temperature of B. So in there I can put 2TB. I'm replacing the RA and the TA with RB. And the reason why I'm doing that is because I can see that they'll cancel out on the bottom down here. So I get on the bottom just RB squared and TB to the 4th. So if I bring this all back down here, LA over LB, then I would find that this is 3 squared is 9 RB squared times 2 to the 4th. 2 times 2 is 4, times 2 again is 8, times 2 again is 16. And that would be TB to the 4th, and then that's all divided by RB squared TB to the 4th. Now the RB squareds cancel, the TB cancels, and so I end up with 9 times 16, which is approximately 144. So I don't know the actual luminosity of either star, but what I do know is that the luminosity of A is 144 times greater than LB. Or I could rewrite this in another way to say that LA is equal to 144 LB. So I have a statement very similar to my original statements where I'm comparing what A is compared to B. Now question 2 is a follow-up to that question, and they ask you, the stars in example question A have the same apparent brightness when viewed from the Earth. Calculate the ratio of their distances. So what they're saying is that BA is equal to BB. Or what I'm really looking for is the ratio of the two. So what I need to do is to divide by BB. And what that gives me is that the apparent brightness of A divided by the apparent brightness of B is equal to 1. Now, I know there's a formula for apparent brightness. The formula for apparent brightness is LA divided by 4 pi D squared, this would be DA squared, over LB divided by 4 pi DB squared. Okay, so let's start plugging in some numbers. First of all, right off the bat, I can get rid of the 4 and the pi. Those are going to cancel. So that leaves me with LA, but I know LA is equal to 144. My mistake. LB divided by DA squared. Down here I have LB, divided by DB squared. So the LBs are going to cancel, and I would want to invert and multiply so what I would end up with is DB sorry, 144 dB squared over dA squared. Now, remember, that's all equal to 1. So what I need to do is to take the dA over to the other side. So I would multiply, and this is all equal to 1. So I would say that dA squared is equal to 144 dB squared. And then I would divide by dB, so now I have dA squared over dB squared is equal to 144. And then what I would like to do is to square root the whole thing. And that would tell me that dA over dB is 12. So if for these two stars to have the exact same apparent brightness, which was our initial starting statement, what would be required is that star A would have to be 12 times farther away. And why does it need to be farther away? It's a lot more luminous. It's much more luminous than star B. And so this would be our final answer for question 2. And then here's our final answer for question 1.